Now let us see some practical problems, practical cases, practical problems, and I will be happy if you can do these things yourself. You can use Smith chart yourself. And what we are discussing, I like you to do this hands-on during the class. If that is not possible, then you can do it after the class. But try to do this during the class. We are going to discuss about matching circuits using lumped elements. You know there are two types of elements. One is called lumped element, one is called distributed element. Transmission line itself is a distributed element. When we discussed about transmission line, we saw that if we take a small infinitesimal section of transmission line that consists of a resistance in series with an inductance and in shunt with a conductance and capacitance. So those are distributed along the transmission line. Resistance is distributed, inductance is distributed. Similarly, in shunted distribution, there is capacitance, there is conductance. So those are called distributed lines. And the lumped elements are the elements that you see. Capacitor you saw, see that is concentrated. Everything capacitance is concentrated at one point. Between two terminals, capacitance is concentrated. Resistance is concentrated between two terminals. So those are lumped elements. So first we will discuss about lumped elements, then we will come to distributed elements or transmission line sections. So let us start with lumped elements. So here what I am doing is, I am showing you a picture of a Smith chart that you can see. But for the time being, I am not going to use this. I will use this data. But since we are discussing Smith chart, so the Smith chart picture is there. On the left hand side, you can see that we have an amplifier. The output impedance of this amplifier is 25 ohms. So Z0, which is the impedance of the amplifier input, I am not concerned. I am concerned with the output. Somehow we have designed an amplifier whose output impedance is 25 ohms. Somehow it is 25 ohms. And this amplifier is connected to a load or is terminated in a load which is ZL is equal to 5 plus J5 ohm. So the load is 5 plus J5, ZL is equal to 5 plus J5, and output impedance is 25 ohm. So if you look at these two impedances, they are not matched, they are not conjugate matched. Therefore, there will be reflection, high amount of reflection. We have to match these two. Output impedance is to be matched to the load impedance. If we can do that, then the maximum power transfer theorem will be satisfied and maximum power will be transferred or transmitted from the amplifier to the load. Power will go, maximum power will go from the amplifier to the load. So we have to match these two impedances. How can we do this matching? Output is 25 ohm, ZL is 5 plus J5 ohm. Simple method, if you look at the circuit analysis, from the circuit analysis, a simple solution you can find out. Look at the picture at the bottom. The amplifier is there. After the amplifier, the load is there 5 ohm. Amplifier output is 25 ohm, so the difference is 20 ohms. So what we will do is we will add a 20 ohm resistor after the amplifier. So the resistance part becomes 20 plus 5 because they are in series. If we add a series resistance of 20 ohm with the load ZL, then the resistive part will be 25 ohm, which is same as the Z0, 25 matches. Then what is left is the reactance part. Reactance is J5. So J5 plus J5 means it is inductive in nature. Inductive reactance can be compensated by a capacitive reactance. So what we will do is we will add in series a capacitance, so that the impedance of the capacitance is minus J5. So minus J5, 20 minus J5, that is the impedance of the added section, added impedance. So ZL plus added impedance of 20 minus J5. ZL is 5 plus J5 plus 20 minus J5 plus J5 minus J5 cancel. 20 plus 5 will become 25. Therefore, we have a perfect match. So our output 25 ohm is matched to the load. So through 20 ohm series resistance and 5 ohm capacitance. Now this type of solution is a novice solution. We cannot use this type of solution. Simple reason is the moment we put this 20 ohm resistance in series, that 20 ohm resistance will consume power. The power which is coming out of the amplifier will be consumed by this 20 ohm resistance as well as the load. So complete power from the amplifier is not going to the load. A part or a portion of the power will go to the 20 ohm resistance. That is not what we need. We do not desire that. Right? What we need is the complete power should go to ZL, which means we cannot have a resistor or a conductance. Resistance or conductance we cannot use because those are power consuming devices. Power storing device you can use because power storage, if that's power storage, that power will go to the load ultimately. But if power is consumed, power is lost. We cannot lose the power, so we cannot do that. So we have to, this is not recommended, this type of solution is not recommended. So what is recommended? What is recommended is we have to match Z0 with ZL or ZL to Z0. So we will consider Z0 to be the characteristic impedance, as if Z0 is the characteristic impedance. That is the first point that we should keep in mind. Then the second point is when it is matched, then ZL becomes Z0, which means ZL by Z0 will be equal to 1. So on this Smith chart, we will look for a constant resistance circle which is passing through 1. If we are on that constant resistance circle, then we are actually matched. So we will look for that. So first take this Smith chart. This is what you have to do. Now if you have the Smith chart with you, take this Smith chart, put it like this. The manner in which this Smith chart you can see, put your Smith chart like this. Then on this Smith chart, locate the R is equal to 1 circle. Okay. I hope you have been able to locate the R is equal to 1 circle. Okay. Now if you have located the R is equal to 1 circle, then what I will like you to do is draw that circle. So use your compass and pencil and draw that circle. That you can easily do. So draw that circle. R is equal to 1 circle. Draw the R is equal to 1 circle. How to do that? You know R is equal to 1 point you locate on the Smith chart. then r is equal to infinity, which is the other end, other extreme end, right extreme end that you locate on the Smith chart. These 2 points, the distance between these 2 points is the diameter of the circle. So once you know the diameter of the circle, you can find out what is the radius of the circle and draw this circle. So draw this circle. I'll give you 1 minute to draw this circle. Okay, and now that you have found out the radius and drawn this circle, draw a similar circle, exactly same circle, which is, I will tell you that you rotate this circle by 180 degrees. Across point 1, point is equal to 1, or across the r is equal to 1 point, rotate this circle by 180 degrees, which means between 0 to 1, in that range, draw another circle. The radius you know, so since you know the radius, draw another circle which will look like this. So you can see the second circle. So one circle was on the right hand side, second circle is on the left hand side. So this we will call as G is equal to 1 circle. Why we will call it G is equal to 1 circle? Answer is, we have r is equal to 1 circle. When we rotate it by 180 degrees, r is inverted. So r becomes 1 by r. 1 by r is equal to G, and r is equal to 1. Therefore, 1 by r is equal to 1. So this is called G is equal to 1 circle. This dashed line circle is called G is equal to 1 circle. So you can draw the two circles. R is equal to 1 circle and G is equal to 1 circle. Draw these two circles on this picture. Let us take another half a minute to draw the second circle. So you have drawn two circles. Now that you have drawn two circles, first find out what is the normalized impedance, ZL. So obtain ZL. ZL will be, small ZL will be capital ZL divided by Z0. Z0 is equal to 25 and capital ZL is equal to 5 plus J5. So 5 plus J5 by 25, that is equal to 0.2 plus J0.2. So first obtain this. ZL, small ZL is equal to 0.2 plus J0.2. Then locate this point. ZL is equal to 0.2 plus J 0.2. Locate this point on this Smith chart. How will you do that? First, locate the constant R circle with R is equal to 0.2. So please do that. Let me give you 15 seconds to locate R is equal to 0.2 circle on this Smith chart. How will you do that? Look at the horizontal line. On the horizontal line, find out where is the point 0.2. So the circle passing through that point is the R is equal to 0.2 circle. So locate that circle. Put a mark on that circle. Okay. So once you have done that, then locate the R with X is equal to 0.2. How you will do that? Look at the rim. On the rim, these values are written 0, 0.2, 0.1, 0.02. All those values are written. So locate that point which corresponds to 0.2. X is equal to 0.2. It is positive, so you will look at the upper half. On the upper half, look for 0.2. On the rim, look for 0.2. So once you find out 0.2, follow the arc which is passing through 0.2 or which is starting at 0.2. Follow that arc towards the constant R, small r circle. Small r is equal to 0.2 circle. Follow that arc and find out the point where this arc and the constant R circle meet. That point is ZL. So locate ZL on the chart as the crossing point of R is equal to 0.2 and X is equal to 0.2. I will give you half a minute to do that. I hope you have done that. So let us go to the next. From the point ZL, move along move on the chart along R is equal to 0.2 circle to meet G is equal to 1 circle. That you can do easily. So from ZL, that you know which is the ZL point that we have found out. Then from that point, we have already located R is equal to 0.2 circle. On that circle, move in the clockwise direction. So we will move in the anti-clockwise direction later, but for the time being, move in the clockwise direction. So move in the clockwise direction along R is equal to 0.2 circle to meet G is equal to 1 circle. So find out the point where it meets the G is equal to 1 circle. Okay. So first locate that. Let us take our 10-15 seconds, 10 seconds for that to locate that point. So using your pencil, draw that. Now name that point as Z1 and find out the impedance of that point Z1. Name that point as Z1 and find out the impedance of that point Z1. Now since we are moving along the R is equal to 0.2 circle, therefore at that point the R will remain 0.2. So Z1 will be 0.2. But Now what we have done by moving away from ZL, we have moved away from x is equal to 0.2. So at Z1, x value will change. So find out what is the x value at Z1. So find out the arc which is passing through the point Z1, move along this arc to the outer ring and read the value. So that value will be 0.4. So Z1 is equal to 0.2 plus J 0.4. Please do this. Let us take another 5 to 10 seconds. Do this. Read this. Z1 is equal to 0.2 plus J 0.4. Okay, and now find out the difference between Z1 and ZL. Remember this is important. Z1 and ZL, difference between Z1 and ZL, not ZL and Z1. So this will be Z1 and the difference between Z1 and ZL. Now Z1 is equal to how much? Z1 is equal to 0.2 plus J 0.4. ZL is equal to 0.2 plus J 0.2. So the difference between them is 0.2 we cancel out. J 0.4 minus J 0.2, that will be J 0.2. So find the difference between ZL, Z1 and ZL. Now this difference is positive. This difference is positive. This difference is positive means it is representing, if we represent this difference in terms of reactance, it will be an inductance. It is positive, so it will be an inductance. So remember this difference being positive will be an inductance. Now as this impedance, and this is an impedance, this difference is an impedance, and addition of this impedance is realized by series connection, and this impedance addition is realized by a series connection because there is we have found out the difference. So difference means if you add two impedances, their resultant is an impedance. When you add two impedances to get another impedance, that means the two impedances are connected in series. Therefore, this is a series connection. So, as this is an impedance and addition of this impedance is realized by series connection, this 0.2 is realized by a series connection. So, what do you mean by this statement? This statement says that we have ZL is equal to 0.2 plus J 0.2. To that we have added plus J 0.2 to get 0.2 plus J 0.4. Since we have added J 0.2 to ZL, that means with ZL we have made a series connection of another impedance. This means that. So a series inductance, this is inductance. So a series inductance is necessary to be added to ZL for obtaining Z1, such that JXL is equal to and J 0.2 or JX1 is equal to J 0.2. So this is what we require. We require a series resistance. Series inductance is necessary. So ZL, after ZL, we have to have a series inductance with ZL. Remember this, the series inductance with ZL is necessary. Now, from Z1, draw a line, straight line, passing through Z01 or Z0. Draw a straight line from Z1 passing through Z0, which is Z0 is equal to 1 or R is equal to 1, small r is equal to 1 point. So draw a straight line from Z1 passing through R is equal to 1 point. R is equal to 1 actually represents Z0. So draw a straight line from Z1 through Z0 to meet R is equal to 1 circle at Y1. Why it is Y1 as we have discussed? This is actually a 180-degree rotation. A 180-degree rotation involves the impedance. Impedance inverted is admittance. Therefore, Z1 will now be transformed to Y1. So you transform that to Y1. So wherever it meets the R is equal to 1 circle, at that point find out what is Y1. Y1 is equal to 1 plus J2 as we have done in the previous case. Similarly here also you can find out Y1 is equal to 1 plus J2. 1 comes from the R is equal to 1 circle and J2 or 2 comes from, this is 1 minus J2, it is in the lower half. So it will be 1 minus J2. This J2 comes from the lower half. Look at what is the value of the arc, where this the arc passing through this point meets the ring. So it meets at 2. Therefore it is 1 minus J2. Do this. Let us take half a minute to do this. Draw this line and locate this. So let us take half a minute. Okay, so we have located that point. Now we have to match. We have reached that point. From that point, we have to come to the center of the matching, means we have to come to the center of the Smith chart. So wherever we are, from that point we have to come to the center of the Smith chart. We have reached that point. That is Y1 is equal to 1 plus J2. So that is the impedance. Now we will move along this R is equal to 1 circle. If we move R is equal to 1 circle, then everywhere on that circle the resistance is 1. So we will move towards the center. From that point, from the point Y1, we will move along R is equal to 1 circle to Z0. Z0 is the center of the chart. So from Y1, move along R is equal to 1 circle to Z0. If we move along R is equal to 1 circle, the resistance will always remain equal to 1. Only reactance will change. Reactance is capacitive here. 1 minus J2. So reactance is capacitive. We will add a capacitive reactance here. So at Z0, there is no reactive part. Z0 is on the straight line. on the horizontal line, so there is no reactive part. Therefore, impedance is matched at Z0. Once you reach Z0, impedance is matched. So matching impedance means we have to reach the point Z0. For this matching, we require an element which is to be added to Y1. So what is that element? Y1 is on the capacitive side, so the element has to be capacitive. Y1 is, since Y1 is on the capacitive side, lower half it is capacitive, so the element has to be capacitive. Addition in capacitance, each short connection of the element. Why it is short connection? Addition in admittance. This is actually admittance. Y1 is admittance. Two admittances are added when there is a parallel connection. Two impedances are added when there is a series connection. So in the first case, Z1 we had a series connection. Here we have Y1, we are adding, therefore it has to be a parallel connection. So addition in capacitance, or actually admittance, is a short or parallel connection of element. So a capacitance with admittance value of J0, J2 is to be added. That is Jx0 is equal to minus J2. So this is a parallel addition of capacitance. So we do a parallel addition of capacitance. So minus j omega c will be minus J2 by 25, or which is equal to minus J 0.08. Similarly, J omega L is equal to J02 into 25, which is equal to J5. So these are the values of capacitance and inductance that we have calculated. Now if you go for 2 gigahertz, you are designing the circuit for 2 gigahertz operation, then J omega C is equal to 0.08. Omega, you know, and omega we can find out 2 into 2 pi, so 4 pi C is equal to 0.08. From that you can find out C is equal to 1.6 picofarad. Similarly, omega L is equal to 5, so omega is 2 pi here, 2 into pi into 2 gigahertz, so 4 into pi, 4 pi L is equal to 5, so from that L will be equal to 0.4 nanohenry. So we can find out the capacitance value and resistance value. The circuit you can see we have ZL. In the ZL, first we have added a series resistance. So to the ZL there is a series resistance that is followed by a capacitance in parallel, so that you can see that is followed by a capacitance in parallel. So this is the long circuit of the impedance, inductance and capacitance. There is no resistance, so there is no loss. So this is the method of matching the circuits without any loss. Why we use these long circuits instead of, as we have seen, if you have a impedance which has complex impedance or complex value R cross Jx, then we can use a transmission line section, then a quarter wave transformer. So why, instead of doing that, why we go for this? Simple reason is, when you look at a transmission line section or a quarter wave transformer, we are dealing with characteristics impedance. Now characteristics impedance is dependent on the shape and size of the circuit that you are using, shape and size of the transmission line that you are using. Now shape and size are fixed. When you are going, there will be standard shape, there will be standard size. So we cannot have arbitrary shape, arbitrary size. Practically, when you come to commercial use or practical use, you cannot have arbitrary shape and arbitrary size. These are all standardized. So in practice, when you design a circuit, only standardized things you can use. Since we can use only standardized circuit, we cannot have arbitrary characteristics impedance. So those are not practicable in all cases. There are cases where they are practicable, but they are not practicable in all cases. So we look for these impedances, lumped impedances. Lumped values of resistance, lumped values of capacitance, lumped values of inductance. These are easily available in market in standard values, so we can use them. Therefore, we go for lumpedness. Okay, with this, we will take a break here. I hope you have done this. What we discussed, we will take a break here. And after 5 minutes, 4 minutes, 3-4 minutes, we will come back and start with the next one. Next one, I will just tell you how to do it. We will not take this time. So you can do that yourself. Next one, I will tell you how to do it. But we will take a break. ପିଲେ କଲ କି ନାହିଁ